from galaxies, nebulae, comets and asteroids, the sun, all of it. Fundamentally, the main tool that we have is to study the light of something.
From a scientific standpoint, why is an eclipse special?
So normally the solar disk is, well, it is always very, very bright. But during an eclipse, the moon comes exactly between the Earth and the sun, and so you'll no longer see that really bright surface, and instead you see the corona, which is this outer atmosphere of the sun. It actually expands out into space and, creates space weather and all kinds of things like this. But the corona, the thing is with the corona is it's about 1 million to 1 billion times fainter than the solar disk. So that it's that really high contrast ratio of if you have something that's a factor of 1 million fainter right next to something else that's that really bright source, it's very, very difficult to observe it normally. And so total solar eclipses are this really unique sort of just cosmic coincidence that our moon happens to be in the right place at the right time, such that we can perfectly block it out, and then we're able to see the corona super easily.
But okay, so the corona, so you can study the corona, but why is the corona special?
It's really just one step along the way of how the sun is influencing basically the entire solar system. So, inside the sun, you've got nuclear fusion powering it, and then you've got these different layers in the sun. Eventually you get to the surface, and that's what we can see normally. So there's tons of telescopes that observe the surface of the sun all the time. But then right above the surface, you have the corona, and it's much lower density than the surface, which is why it's so much fainter. And then that material actually is unbounded. So unlike the surface of the sun where it kind of just stays there, the corona actually expands out into space and fills the entire solar system. So if, from a sort of a selfish motivation, we're interested in understanding the corona because any dynamics that happen in the corona will propagate outward and potentially can impact the Earth, other planets, if we have spacecraft, or even if, in the future we want to go to Mars or something. This is the sort of thing we have to think about of how is the sun impacting the solar system. And the corona is really this sort of nexus point where a lot of that stuff gets started. So it's sort of simultaneously this really important region for understanding how the solar wind is going to be formed and how the sun is impacting the solar system. But also it's one of the most difficult places to observe.
Is there something that people right now by studying eclipses, we are trying to find this specific thing out? Or is it more just set this up and let's see what we get?
It's definitely more the latter, which is a little bit different. In most of science, the method is, okay, we have this hypothesis, we want to make a very particular observation to get a very particular result. And we do that to some extent, but in a lot of ways, we're at the mercy of whatever the sun decides to give us on a given day. So, so the eclipse, they only happen about once every year to year and a half or so. And so that means we're really just getting one snapshot, and they only last a few minutes. So you're really just getting one little snapshot at one point in time, every year or two. But because of that, we end up finding things that we don't expect, maybe there's a really cool coronal mass ejection and it behaves in a way that we've never seen before. And so we can study that. Fundamentally, though, we know what the corona is going to be doing in the sense of we know what metrics we can use to study it. And the main thing are these things we call emission lines. And so this comes out of something out of atomic physics, where different atoms, different ions and elements have very particular colors of light that they'll interact with. And so we know what are the primary atoms that are in the corona that we're interested in. And we know what that can tell us. We know how we can measure temperature and density and magnetic field and something called the Friesen distance and various other physical properties. We know that these lines will give us different information about this, and we know exactly what color they're going to be. It's always going to be the same because the atomic physics never changes. And so we go with these cameras with these particular filters, knowing full well we'll record this line that we're interested in. And then really it's then when you see how bright was the line, how does this line compare to a different line, that's how we then can get deeper down at the different physics that we're studying.
So you can tell by the colors essentially how much of an element is in the sun.
Exactly, yeah. And this is what we do in all of astronomy. So literally any area of astronomy from galaxies, nebulae, comets and asteroids, the sun, all of it. Fundamentally, the main tool that we have is to study the light of something. And so we can understand the different compositions, temperatures, densities, magnetic field, etc. We learn that from studying the light. And that's observationally how we do things.
What are some things that we have learned from eclipses? I don't know how your history is necessarily, but are there things that we'd say, because of an eclipse, we figured that out?
Historically, going back into the 19th century, there were a lot of astronomers who would travel to eclipses, and they would very diligently make drawings of the eclipse. And I think usually they would have a team of a few people who would take notes and draw as much as they could. And then they would compile all of their notes to make one master drawing to be like, this is our best guess of what it looked like. And if you go back to those data, it's actually seems pretty accurate based on, it's not perfect, of course, but it's relatively representative of probably what it really looked like. And then the famous one was in 1869, where they observed with a prism for the first time. So you basically took an image of the corona through a prism, which breaks it into the different wavelengths, the different colors of light. And that was when they discovered this new line that had never been seen before, this new emission line that was in the green at about 530 nanometers. And this had never been seen before. And, in around the same time in the laboratory, chemists had been burning things and looking through prisms, and they had identified many of these different lines, like, oh, this one corresponds to calcium, and this one is magnesium, and this one is lithium, and so on. But this line that they found in the corona had never been seen anywhere else, so they named it coronium, because they thought, oh, it's a new element. And actually, this just before that, I don't remember the exact year, but that's actually why helium has the name that it has, is that helium was first seen during an eclipse with the same kind of observation, and they saw these lines they'd never seen, and they said, well, let's name it after the sun, Helios, so that's helium. And so that was actually coming from a part of the corona we call prominences, whereas this coronium line was coming from the corona, hence why they called it coronium. And then it wasn't until many decades later in the 1930s that quantum mechanics kind of came to maturity, and they realized that, no, this isn't some new element. It's actually just iron, a very, very well-known element that's all around us, but it's been ionized 13 times. Some of my favorite papers are going back and reading the ones from the 1950s and 60s when they really started getting better and better instrumentation, and they measured all kinds of things about the polarization of the corona, about the fact that there's also a lot of dust throughout the solar system that makes a good amount of the light. There's the electrons in the corona that re-emit solar light, and there's these ions. And so there's some really great papers more than half a century ago where they were discovering all of these things.
Will there always be eclipses?
That's a very good question. So basically, the moon is actually getting farther away from us over time. And this is because as the moon orbits the Earth, it actually creates the tides, right? That's why we have the high and the low tide every day, or twice a day. And that the tides actually kind of rub on the Earth, and there's some friction there. And that actually applies a torque to the Earth-Moon system. And so it actually slowly flings the moon away from us. I won't go into all the physics of it, but basically the moon is, because of the tides, is slowly drifting away. And so if you wait a long period of time, eventually the moon will be too far away where all of the eclipses, it won't be able to fully block the sun anymore. Now, if you run the clock backwards and say what was happening when the dinosaurs were around hundreds of millions of years ago, the moon was quite a bit closer. And so actually you would have had total solar eclipses that would last much longer and would have occurred much more often. So the dinosaurs were probably treated to, a few times a year that they would see a total solar eclipse, and it might last, many, many minutes, as opposed to now where we're, getting just a couple of minutes. And sometimes, like what happened last year across the US, there was an eclipse, but the moon was a little bit too far away. And so you had what we call an annular eclipse, where you get the ring of fire effect. Part of the problem is that the moon's orbit is tipped about 5 degrees relative to the Earth's orbit around the sun. So there's certain times of year where the moon and the sun and the Earth line up perfectly, and there's other times of year where the moon passes above or below the sun. But certainly we are super lucky that we have a moon that is as big as it is, which is much, much bigger than any moon of any other planet that we know of, relative. So the relative size of the Earth and the moon they're far closer in size than any other planet moon system that we've discovered. So it's probably a cosmic fluke that we have this coincidental alignment. And I've actually heard, jokes where people say, in the far future, if humans really do colonize the galaxy and spread out to different solar systems, then eventually there'll be tourism to come back to the Earth to see an eclipse, because it will be something that they won't have on any of the other solar systems.